So welcome, everyone. This is the second talk in a series that my colleague Bhavik Patel and I are trying to start highlighting people internationally who work in the area of chemistry education, particularly focused on analytical chemistry. And I'll drop into the chat the registration link for the June talk. But today I'm pleased to welcome Patrick Thomson, who is a teaching fellow in pure and applied chemistry at the University of Strathclyde and is interested in chemical education research, especially laboratory education. He's going to be talking with us today about balancing the kinds of figures of merit that we might hope for in our analyses and experiments with affordability in outreach and teaching. So welcome, Patrick.
No, thank you very much for the sort of kind introduction. And I'll share my slides and get my other screen set up again, which isn't working the way it was a moment ago, which is helpful. Okay, there we go. Okay, am I coming through fine? We can see the slides and the screens. And okay, yeah. So I think I'm not going to talk for very, very long here. What I'd like to do is kind of get into potentially a little bit of a discussion afterwards, see where this has sparked some ideas. But yeah, I kind of I'll talk a little bit about where this has come from as well. But this idea of I work in, well, okay, I'll just get into it. So I'm from the University of Strathclyde, which is in Glasgow. It's one of our bigger, older universities in Glasgow, has won a bunch of awards that I'm not going to labour the point, but because I'm following our recommended procedures, I have to have them all on the first slide as well. But by and large, um, kind of Glasgow is the largest city in Scotland. I am not from Glasgow. I grew up in the area, but I've worked in Glasgow for almost 10 years and come to accept a certain style of reverence in the city that decides to just put a traffic cone on the oldest statue we have because it's incredibly dangerous, and then the council keeps taking the cone off. We work right, the university is right in the center of Glasgow. This is George Square, which is our kind of central older area. And one of the university buildings, this little red sandstone peeking out there, is actually one of the buildings I used to work in here. And Scotland also has the kind of unique, it's a small nation, spirited nation, and we have this kind of unique signifier, I would say, of being one of the only places in the world, if not the only place in the world, where Coca-Cola is not the number one best-selling soft drink, thanks to this delightful fellow that hangs around rotting the teeth and brains of successive generations of young people in Scotland. And our department's got a range of kind of specialist degrees, and the notable one and the one that's most relevant is our forensic and analytical chemistry degree. So we have got specialist kind of forensic science units, but also a lot of analytical chemistry. It's one of the older, larger, and more well-regarded ways, trainings for analytical chemistry in the UK. And we have lots of dedicated specialist analytical chemistry colleagues that take people on that journey through those degrees from second final year into specialist master's courses into kind of like fire analysis, footprint, and like all that lovely forensic chemistry stuff. But I kind of sit right down at the other end of that university journey. I'm head of first year chemistry, so overview of all the programs. I'm also head of the first year lab, so I'm in every single lab, and I'm teaching. I have TAs with me, but I'm face to face with every student every week in our labs. And our intake is only about 140 students a year, but because of the size of Scotland, that's about a quarter of all the chemists in the entire country. So we do have this kind of impact on our kind of local landscape. But this is where the wheels start to come off a little bit as far as my alignment with the meeting is concerned, because I am a very approximate person, as you might imagine. A big part of my job and a big part of what it takes to do parts of my job is to be approachable enough to make people feel assured in that difficult transition to university, which means being quite a hand wavy person sometimes, which is because I'm an organic chemist. I'm so sorry to have intruded into the meeting, but I was screened by your organizers, and they did say it was okay, more or less. And I'm going to talk about two specific projects, lab experiments that I've developed. Me and my student team have developed that are really focused in this area of analytical science, and we use them either for outreach, in-reach, or in our first year teaching. So in reach, they come to us, outreach, we go to them in our teaching labs as well. So I'm going to talk about these kind of two projects and where they came from, what inspired them, and maybe some things that some ideas that you might be able to take into your own practice, if not the experiment themselves, then some parts of the way that we designed it. Because I'm going to like try and weave in a little bit of my own teaching philosophy and design philosophy and how I do my education research and where that kind of research philosophy comes from as well. Because I'm an action researcher, I do education research because I want to make my teaching better and I want to make other people's teaching more exciting, more engaging, more accessible. I've been doing lots of work that I'm not going to talk about in areas like anxiety reduction, accessibility, affordability. Piece of work on the left. Everybody was coming back from COVID. They didn't want to sit exams in a closed book hall anymore. People were getting so anxious. They were contacting us before term even started to ask what the exams would be like. And at the end of the day, we just let them take a crib sheet in because it reduced their stress by like 95% and they all loved it. And the grades didn't really change. So call that a success. We also have done work looking at just the financial landscape is a bit grim in secondary teaching, possibly worldwide. And we did some work looking at supporting schools as they sort of navigated the return of a costly curriculum aspect in Scotland and found out some pretty severe things there that we'll come back later. But the philosophy that kind of underpins it, and I found this, and maybe you see this in yourself, in junior teaching colleagues, is you want to say, if you're building a teaching activity, and you're going to make some pragmatic compromises for cost, for speed, for simplicity. Do those compromises offend you more as a scientist or an educator? And hopefully, what I'm going to show you is some things that might offend you as a scientist, but which hopefully might make sense as an educator. Now, I'm not talking about leading students down dark misconception paths and undermining their ability to use equipment properly in the future. But there are sometimes our diligence and our expertise gets in the way a bit, especially when we're teaching people at the earlier end. So there are some things in here which I would describe as horrifying compromises that I made to the teaching materials that made them 10 times as accessible. And that hopefully is that philosophy is going to be kind of woven through here a little bit. So the first of two projects I want to talk about is we wanted to analyze paracetamol, which it turns out lots of people have done before. There's this meta-analysis that's almost 20 years old, and it's got something like 300 or 400 different methods that people have developed. I don't think chemistry or analytical chemistry might not have a Drosophila or a model organism, but if we did, it might be paracetamol. It's probably, potentially, one of the most analyzed organic molecules out there. And please argue with me at length about this in the aftermath, because I'm going to use that quippy little thing if I ever write this up. But it really was astounding. I said, let's try and improve on the gold standard in schools, and we found that there were hundreds and hundreds of less accessible ways of doing it because not every school has got an HPLC or an NMR or any of the more kind of standard equipments that we might have. So this is a project that we were looking at for mostly an outreach to help schools, secondary schools in Scotland. And out of this, actually like the oldest, cheapest, and least accurate method in this entire kind of body of knowledge around paracetamol analysis is the one that tends to be used in schools because it's also relatively more accessible. That's a method where paracetamol, it's an amide, has an amide bond in it. It undergoes acid hydrolysis and then is titrated with a redox titration reagent, cerium ammonium sulfate. So that 4-aminophenol, you get it from hydrolysis. It's redox active. You can run run a hydrolysis with paracetamol in it, run a blank without any in it, titrate them both for redox activity, and then compare the values. And that gives you, with some calculations, a reading of how much paracetamol you start with. It's the kind of thing that's fairly immune to background excipients as well, so you can take an off-the-shelf capsule, grind it up, and get a fairly decent, accurate reading of how much paracetamol is actually in there, or if the pupils have made the paracetamol themselves in a lab experiment, we can do this analysis. But for schools, it's still too expensive. The cerium ammonium sulfate, we're talking on the order of, if you buy the calibrated reagent, if you make it up yourself, it's a bit better, but not much. But if you buy this in, we're talking £1, $1 per titration. Like for a school with a class of a few pupils, that becomes untenable when your entire chemicals budget is a few £100s for barely covering things like gloves, sulfuric acid, HCl, sodium hydroxide, and that's it for the year for an entire school's worth of chemicals. We're talking situations of quite dire financial circumstance. So unless a school already has some leftover reagent, they're just simply not doing this experiment anymore. So this is where we came along and thought, maybe we can improve this a little bit. The gold standard, I'm describing it as the least accurate method in the literature, but it's not terrible. Now, the maths is wrong here. Those that are reading ahead, it's fine. It's fine. I'll get to it there. But say the student runs a titration on the paracetamol analyte. They get out a titer of something like 20 mil with as close as they can get it. The background might be 1 or 2 mil of blank, and then they subtract it out, and then If you break the rules of how you actually are meant to combine errors and just trivially go, let's make it as bad as possible, you still find that the students are, in theory, arriving at an error of like less than 5%. So they're still getting reasonably accurate results out of this. And we do actually run this exact thing, this redox titration. I'm doing it again in a couple of weeks' time. We bring pupils into our department and have them kind of spend a week as a chemist and make this, and then spend a week analyzing the paracetamol by various methods, including this titration. Um, but as I said, the schools can't even afford these reagents. This is a table clipped from the paper I talked about earlier about the school costs. We asked teachers, where do you get your stuff? Now, a lot of people were saying, oh, our technical staff can make a financial order. Over half of the schools in Scotland are asking pupils to spend their own money on stuff to analyze or reagents. Now, bring an aspirin to school and we'll grind it up and analyze it. It's a few pennies, but it's the principle. This is a kind of I think the canary in the coal mine, a bad sign that we are having to resort to this kind of thing to make chemistry happen. Bring in your favorite energy drink and we'll extract the caffeine from it. But we're still asking pupils to spend their own resources on these things. And this is an open access paper. You can have a little read about this. I'm happy for the slides to go around afterwards then, if necessary, or take a picture, have a chat. But so we kind of said, okay, let's make this a little bit cheaper, right? So we'll try and make this a little bit cheaper. What else can we analyze in here? And the literature was no help because the redox titrate, well, it might have been, but the redox titration was one of the simplest methods in there, one of the oldest ones. So there's also some other useful bits in there. I've kind of neglected it so far, but the acetic acid is a titratable acid. There is something in there that you can meaningfully titrate against. But there's also the acid catalyst, and it's a catalyst, but there's about 10 molar equivalents in there to get the hydrolysis to even go. So that's not great. There's also some acidic protons on the actual other partners as well, and the starting material. So quite a few confounding factors that are going to make this maybe a little bit difficult to analyze. It's probably why so many people did it by the redox method, because all those other things aren't redox active, and it's a wonderful way of isolating them all out and not having to worry about them at all. So Mella spent her entire master's project working on this problem and tweaked the conditions and tweaked the circumstances, and it was a lot of work to get something that was really robust and reliable, but we managed to get it down to something that could work in a school hands. So what we'll do, we'll take a sample of paracetamol, hydrolyze it with a slightly less sulfuric acid, but we still get the reaction. The reaction needs to run in about an hour because that fits into certain classroom timetables. So we hydrolyze our paracetamol sample with about 10 molar equivalents of sulfuric acid, which is the least we can get away with, we think. Titrate it out with sodium hydroxide phenolphthalein, run another blank without the paracetamol in it, do the same thing, add in a bunch of sulfuric acid, reflux it for no reason, well, comparative reasons, and then titrate them both out again. And in the hands of pupils and students, and we've seen this now, the typical titer of the paracetamol might come out to be, say, 21 mil. The blank is now 19, which is a little bit of a problem for accuracy because you've got two big numbers that could be doing this, depending on how accurate the pupils actually are. Even under the best of circumstances, even if the pupils are really, really good and they get their errors down, we're still looking at, again, worst case bad calculations. We're still looking at roughly 20-25% error. It's rubbish. It's really, really bad. But it's also 100 times cheaper. And it works. It works well enough that you can track pseudo first order kinetics of paracetamol hydrolysis. It's not great, but it works. So we can actually, and I haven't got the other data here, but we can even do things like pull out paracetamol versus excipients. As long as you're not hydrolyzing something that happens to hydrolyze to acetic acid, it's actually fairly accurate. Over-the-counter medications with starch packaging or something like that. It is, I want to emphasize just how awful, just how rubbish, how non-accurate this is, which should offend you as a scientist. No one who's a scientist would ever pick this method to analyze paracetamol. But it gets it into the hands of way more schools and way more pupils. And procedurally, mechanically, it functions exactly the same as the better, more complicated, more active redox titration. People do some refluxing. Ooh, it's nice. Bit of feels like organic, feels like synthesis. Then they do some analysis. The titration changes color halfway through. They write down some numbers. They do a calculation, and they get out a measure that says their sample was kind of accurate, good enough. Right? Nothing about that operation or how exciting or otherwise the teacher could make it has changed, but it is a lot more accessible. And the way that we've done this already, we have incorporated this. We've got a database of teacher support. This is available for free to all teachers in Scotland, and anybody here can just sign up to it and go through our full database as well if they want to. It's embedded into the Scottish curriculum in some places because we've been doing this kind of schoolwork for so long. And schools are already using this because it's what they already have in the cupboard. In this kind of time of financial crisis, what you already have in the cupboard is the only thing the schools have. And as I said, it's much less accurate and it's good enough. And we will write it up at some point because, like those of us here on teaching track careers, I suspect I have officially no official requirement or workload allocation to do any scholarship in the area at all. But we like this, and teachers are using it, but we'd like to get the word out there pretty soon. So keep an eye out. We'll write this up at some point. But I wanted to start off with the paracetamol project to kind of illustrate that principle a little bit, to really do something that's fundamentally offensive to me as a scientist, but which upsets my kind of finer, accurate sensibilities. But it gets more material into the hands of more people more accessibly. And we kind of picked this up and ran with it in our second project that I'm going to talk about, looking at colorimeters and spectrometers in particular. And this is an approach that we did not invent. We have built a bunch of colorimeters out of Lego, right? It's a common thing. It's been published. It's been around in the literature for ages. You've probably done it. Probably more than one person in this call right now has a teaching lab that has a spectrometer made out of Lego in it somewhere, right? Big history of this. Wittingen have been doing great stuff. Like, you can pull fluorescence out of them now, put 90-degree angle emitters and detectors. John O'Donoghue's used this in like every single school in Ireland. There's a really big history of this kind of stuff. I got interested in it. Thank you for dropping the link in. I got really interested in this stuff during COVID. In the first weeks of the lockdown, I got a bit manic at home and was like, what can I do? And I ended up getting this setup, which is a opaque plastic squeezy pipette bulb full of diluting juice or orange squash Kool-Aid. Um, and I still got pretty good results out of it for a calibration curve that graph's not come out very well, 0.995 r squared value. For I was diluting, I was making up my dilutions using a plastic measuring cylinder I had stolen to use for shots. So um, it is really robust, really simple. And the thing that kind of works in these designs in particular is that an LED is obviously a light emitting diode. It emits light. It's great. It's monochromatic-ish. But LEDs are also monochromatic-ish detectors. Now, they're rubbish, but they're good enough. But the other thing that they do is that response is almost entirely linear. So unlike a photodiode, a photoresistor, you've got a resistance going from like 500K in the dark down to something, or it's the other way around. I don't know because I never used them because it seemed like a load of faff. Because you probably have to program a microcontroller or use a computer program to translate the resistances into voltages. It's a nonlinear calibration scale. And that seems like a lot of fun if you want to also do the programming. But I kind of plugging something directly into a voltmeter was about my limit of measurement science. And I found that this approach was just a lot more feasible for the stuff that we were tinkering with. And there's lots and lots of designs around here. Fundamentally, all you need to do is hold an LED next to another LED and have a cuvette in the middle of it. Yeah, exactly right. Color matching, that kind of stuff is kind of. We'll look at that in a second. But we've got this. Yeah, I played around with all the LED. These were LEDs I'd actually stolen from my own school and had in a box in the loft for almost 20 years. And then again, it was COVID. What else was I going to do? But lots of different designs. You just need to hold the LEDs next to each other with a cuvette in the middle. And people have done 3D printing designs. They're brilliant. They're amazing. Sorry, yes. People have like carved these out of wood. People were injection molding plastic, gluing things together in the 90s to build spectrometers like this. But I think particularly with the advent of Technic blocks that have just the right hole in the middle, Lego kind of emerged at the forefront of this because it also adds that kind of manipulable aspect to the experiment, especially at the simple level where you're working the pupil. It's also quite appealing to the students, and all the kind of scholarship out there in that area supports it. And it's really good stuff. This is Lisa Wittingen's. I'm sure I'm butchering the name, but really elegant, engaging designs of Lego spectrometers. You see, she's got a design where you've got two cuvettes there, so you can do that thing where it's like, oh, it cuts out half again, half again. You show that kind of light diminishing over time. Really simple design with a battery, an LED, and a voltmeter. And the standard cuvette, the standard UV cuvette, is a little bit smaller than a Lego brick 2x2 hole. Which you can see in that design, they've got these kind of little square trays that the cuvettes are standing in. And those square trays are made by chopping the top off a Lego brick with a hacksaw, which is a little bit upsetting to me as a hobbyist and a toy aficionado. And really, the inciting incident for our project that we developed was I wanted to try and not have to do this. I didn't want to cut my Lego bricks in half to build a spectrometer. So, myself and another student, Matthew, for the last year has been working on this stuff, and we said let's have a little bit of a play with this. We've done some other stuff as well with it, but it started with trying to eliminate this need to chop the Lego bricks up. And it turns out there's a bunch of different Lego bricks that have got little stipples on the side as well as just on the classic Lego studs on the top, but you can also get one with studs on the side. Those studs on the side mean that it really brings this design in and constrains it into almost exactly the same size as the standard outer diameter of a disposable plastic cuvette. So this is the design we've ended up coming up with. Like it's a handful of bricks, like 12 bricks or something. Black plastic, Technic bricks to hold the LEDs as well, and a plastic cuvette just fits directly into there snugly. It's not moving around. The signal is solid, constant, really nice. Like snug. Again, I keep coming back to that. We went through a lot of prototypes and came up with this one that relied on bricks that weren't too expensive and available from the kind of standard pick a brick approaches. We've sent a bunch of these out to schools already. I've been using these in my teaching lab for 2 years in the hands of an average undergrad. And they're getting really, really very good results. And the eagle-eyed will notice this absorbance graph goes up to 2, which is the no-no. But even so, even going out with that region, and even on the kind of horrible compromises I'm going to show you later, it's still really, really good data in the hands of students. But I wanted to avoid cutting Lego bricks in half, but as again, as a chemist that is slowly becoming an analytical chemist and slowly appreciating the value of precision and accuracy, there are some things about this design that are really, really upsetting, even though it works really, really well. So again, I want to sort of shield myself with this a little bit. If it educationally works, then hopefully we're okay. So first of all, I just don't bother covering for background light at all. This thing sits on the open bench. And this was a photo I took in my kitchen yesterday, 27.6 millivolts off a tap water reading. I throw a bunch of black material over it, 27.6 millivolts. The background light error is smaller than the accuracy of the reading on the voltmeter, and it's certainly smaller than student-introduced errors. So why bother, right? Okay, people are going to learn later on about proper designs and shielding and backgrounding and from an actual instrument that we can't afford. But with this design, we're cutting it down to that sort of minimum viable concept of light pathing and cuvette arrangement and getting really good results out of it as well. The other thing that we do that's really horrible, and of course, you know, Fourier transform things, is that we use just white light. Okay, white light, but polychromatic light. So I've sort of shuffled this around a little bit, and I'm sorry for the colors not matching with the actual described colors, but we use a white-ish LED. That's the sort of green line that I've elevated off the baseline here, which has got a very sharp spike in the blue because it was very cheap and quite harsh lighting. I've got my blue LED using it as a detector. Now, when that blue LED is emitting blue light, it's that little helpfully orange peak there that peaks at about like 460, 470 nanometers. But the blue light is actually sensitive to a lower range. And the way we did this, we actually literally stuck this inside a fluorimeter and shone wavelength after wavelength on it manually and measured its response and got this curve out. This blue LED is not a monochromatic detector. It's kind of half width, half height width is something like 80 nanometers wide. And yet it gives really, really, really good linear results with most of the compounds. So even though you would absolutely not design a functioning instrument like this at all, you would use laser sources, you would use monochromators, you would use diffraction gratings, you would do all of that stuff that just doesn't seem to change its utility or wouldn't make the slightest bit of difference to a student learning the principle of the Beer-Lambert law for the first time by hand on an instrument they built themselves in 5 minutes. And the result of that is that the whole unit, including the voltmeter, is like £5, £6, £7, not very much money at all. The cost of 2 coffees, less than 2 coffees actually these days. It even functions on several wavelengths because you can use LEDs, a red and even a yellow and red LED will also be sensitive to different parts of the emission spectrum. And we can even have this as a kit where this is the next stage of the development to swap out the detectors. So previous designs have used like 4 or 5 different emitters, but 1 or 2 like a single detector, whereas we're using a broad spectrum emitter, but single different wavelength detectors. Now, of course, like if we had fluorescence or Raman scattering or something, of course, the fact that it's a polychromatic emitter would be a problem. But like, it's a rubbish instrument. It's not good enough to detect any of that. So it's just going to detect basic dilution series. And as I said, this is exactly what we get with the student data. We actually, this whole experiment is just a trick to teach them how to do serial dilution accurately before they have to do it on transparent solutions. But again, the students are getting really, really, really good data. This isn't even cherry picked. This is I pulled this at random from a student's reports and just copied their numbers down, and it just happened to be one of the really, really good ones. But even so, the average is still very, very accurate for this. So cheap as it is, it's still giving decent results with many, many things that everybody builds into their designs that are actually completely unnecessary. Background light, blanking, zeroing, all that kind of thing. So we've ended up having a lot of success with this at an outreach event. We've also it's not sufficient that it's doing Lego as well. We're also using it on what I would describe as a socially relevant analyte because this drink is bright orange, the same color as the can. It wasn't a throwaway reference earlier. Every year, 150 students, 140 students are using this color emitter to reverse engineer the exact concentration of horribly artificial azo dyes in this soft drink, which they all know and love because the majority of them have Scotland as their born or adopted homes. And the students think it's their favorite experiment in the lab. The cognitive load is manageable. I could spend a whole separate thing talking about cognitive load theory, and I'll gladly get into it in the conversation. But a bunch of this is manageable. The TAs really approve of it as well. Like they either really like it or they like it. And when we even again we're working on publishing this at some point eventually, but we even put together a little sort of formal evaluation instrument on some conceptions of theories, principles related to the Beer-Lambert law and dilution and spectroscopy, and the improvements were going from like 75 to 95% utility on one measure and about less than 60 to 90 on another. So the students are learning about the practice and principles of colorimetry in this on a piece of kit where the entire lab cost much less than a single instrument. So entire groups are able to do this at once. So hopefully what I've done is I've shown you some very, very simple outreach teaching activities that can work on a real shoestring budget. You're not spending a long time building equipment or sourcing equipment. And hopefully it's got the pragmatic compromises that are the type that will offend you as a scientist and not as an educator. So there's this wrestling, there's this balance between our monologue, our scientist monologue that says we have to do it properly, and then the teacher monologue that says the kids will get confused, burned out, they're not going to like this, they're not going to engage with this. And I think if I've done anything, I've tried to find a balance between those two areas and said, what's feasible? What can I do? And more than that, what can I do for other people, for schools, for other teaching staff in a way that kind of help them find solutions that kind of pragmatically work for them? So that was kind of everything that I had to sort of run through. I know there's been some comments and kind of chats that we'll get into as well afterwards, but I'm going to sort of draw it to a close there and stop sharing my screen and sort of turn it over to all of you. So thank you very much. And if you've got questions, very happy to get into it. Yeah, yeah, go on, go on.
Thanks, Patrick. If it makes you feel better, I always describe teaching as lying so as to leave the correct lasting impression. So don't feel
Perfect.
bad if it gets it across. A couple of comments and questions. One is, I think as analytical chemists, we're too caught up with below absorbance of 2. A lot of commercial spectrometers can push 6.
Mm,
Now, other things then happen, stray light, not stray light, but rather scattering and whatnot. But, like I think we get caught up in 2. At the same time, I'm very impressed you can get to 2 with an open air. Have you tried pushing it harder?
mm. Not much harder than that. I think from memory, our maximum, the raw readings we're getting are on the order of say 60 millivolts, and our instruments are only reading to zero point 0.1. So
Ah,
that's already bringing you down to 0.6 millivolts, which is like more than a 10% error. It was lucky that it was working there at A equals 2. I haven't gone higher. I feel like somebody's
okay,
tried. Um,
okay.
but yeah, that's
But
that's
but it may
about the
be the
limit that we've got.
multimeter rather than the spectrometer.
Yeah, yeah. Actually, if you have better LED pairings, the raw voltage readings can be a little bit higher. So John O'Donoghue's instruments are reading, 700-800 millivolts, or you just have a better voltmeter that has a higher internal resistance. Then you can get another decimal place out of the accuracy potentially. I actually like it that it's not too accurate, because then that missing decimal place on the fourth order covers a multitude of sins like the background light or the scattering, for example. So no, I haven't pushed it that much further.
Okay.
Yeah, also a really good comment from Diana as well about the LED colors. Yeah, my student did a lot of like work on matching the LEDs and buying in different flavors of them to see how some of the colors of silicon just, or the responses just aren't very sensitive to incoming light. But we've got a good like 2 or 3 different detectors that we can swap in. Ooh, yeah, no, this yeah, no, thank you from Kirsten talking about the Lego. Yeah, no, there's a reason that half of my social media recommendations are brick build videos. I'm very much a fan of that. No, Matthew, the student, was attracted to this by the Lego as well, and we kind of sat down and said we can do better than cutting the tops off these. So the earlier designs actually involved Technic bricks within the kind of the little plugs that then push out a little bit, but we found the sort of 2x2 stud faces were a little bit easier. But yeah, there's definitely people we can sort of lean on for future designs. Oh, sorry, go on.
I was going to ask if you could say a little bit more about what you've learned about cognitive load on these experiments. I've done some work on student-built instruments as well, and I think one thing that's really nice about them is that the students can see what's actually happening, because the instrument's very simple and it's sort of stripped down and very obvious what's going on. And so I was wondering if you could say a little bit more about what you referenced about cognitive load
Mm,
and how the students sort of encounter this project
sure,
intellectually.
sure. Yeah, so I've not applied any of the cognitive load stuff that I've done to this experiment in particular, but I've been very interested in that as a design principle for things like integrated instructions. So reducing the extraneous load of going from workbook to written to diagram to back again. This one has actually kind of got a lot of staging in there. So the students build the instrument using a separate tiny little booklet that has like the Lego page booklet instructions on it. They're only on that one source. And then they switch to another source that just takes them through the calibration and then switch away again. So I'm minimizing the amount of instruction integration that they're flipping through. Of course, because it's me, I've built some guided inquiry elements into it. So I'll do things like they'll plot the percentage transmittance, which is a curve, and they'll plot the absorbance, which is a straight line, and I'll just say like which one's better. And they're doing all of this in the lab as well. So those are actually adding cognitive load in, but I'm sort of recognized correctly, as it turns out, that the instrument itself is like a super manageable thing for them to do because it's just Lego and cuvettes. The biggest place that I actually see them struggling is it's in other experiments, honestly. And it, yeah, I could talk at length about cognitive load, but I guess the upshot is I had a lot of the cognitive load design principles in my head when we wrote this experiment up in the first place. Mm. Yeah, no, good comment. Diana there, yeah, as I rightly suspected and predicted, a lot of us are doing this kind of stuff already, particularly the kind of build and design. And of course, I'm working at this in our first year, so people are 17, 18 when they come to us in the university. Students in our second year and beyond are doing more advanced versions of this, building instruments that are involving kind of enclosures. They're assembling pre-made parts that are a little more complicated, not quite sort of laser table level, but not far off. Um, that's quite a, I can't get that. Oh, that is, yes, no, absolutely brilliant. Yeah, exactly the same kind of thing. Anything that just kind of holds the LEDs in the right arrangement is just really spot on, and it's a great kind of evergreen design. I can encourage anybody to have a play with it, if they've not. And yeah, different flavors and colors of color. We actually, when we were developing this, our initial thought was to try and use some yellow detectors and or yellow or red detectors and get some chlorophyll in there, but the chlorophyll extractions are solvent based and glass cuvettes, and we're talking kind of 200 kids doing it. And we ended up trying to extract chlorophyll into water and get it non-turbid, and it was just going to be too much of a mess. Because the other genesis of this, I wanted it to be a citizen science project. I wanted them to bring in analytes from home. Now, unfortunately, again, costing, So I was thinking tap water, but everywhere in Scotland's got really, really soft water. So all you'd find is no calcium, no calcium, no calcium, no calcium, for the whole year, and it just wouldn't be that interesting. So in the end, the analyte is the same for everybody, which is iron brew. Um, oh, Lego packs to buy to build these kinds of things. I ended up for bulk buying, I ended up using a couple of the sites that sell bricks directly from kind of part out resellers. Bricklink I used. I'm aware of Brickowl as well. I think that's mostly EU. But the Lego Pick a Brick itself has a lot of these in it, and we're talking like 25p a brick, which for putting together a set of instruments is like a few pounds, a few dollars for the clutch of like for all the 12 pieces it is in there. And if you're buying a larger kit, you're going to kind of spend more on the bits you're not using. It really is just about getting those bricks that intrude into the space to make them snug. I tried doing what's the illegal building techniques of doing side-ons and then sliding them in, but it didn't quite pan out. So there, I could get massively into the Lego designs, but basically you can do more with the Lego. Sure, anybody that's built one of these has noticed the kind of cuvette rattles around a bit awkwardly in the 2x2 slot. Yeah, no, we wanted to do that. Really wanted to do that. Breadboard spectrometer, shoebox enclosures. Yeah, no, all this stuff. As soon as you start getting more accurate readings, better data, better designs and instrumentations, you kind of start bringing in those, escalating those people to levels where you get the kind of more stuff on. But this really just sort of breaks that ice with that technique. And honestly, it's in the middle of a fairly punishing lab sequence. They just needed a break and do something a bit fun. Like, welcome to university. It's really difficult. Everything's different. Here's a bag of Lego. It's just quite a fun approach. Yeah, no, I started with Bricklink and just never went anywhere else. I was ending up pulling maybe £2-3 per set when I was buying it. I foolishly offered to give away one free to every school. So we did a CPD event for school technicians. So we're supporting teachers for years, but the technicians are the unsung heroes of the school technical room. And I said, oh, I'm going to give one of these free spectrometers away to every delegate. And then we had 80 people sign up to it. So I was in the physics department soldering the rigs for about 2 straight days. But when I ordering the Lego on that kind of scale was, £100, £150 for enough bricks for 100 sets or something. So yeah.
Patrick, maybe shift gears for the titrations that they do in high school. Do they use
Mm.
burettes or balances?
Burettes. And balances are a really interesting one. I think for various historical reasons, the UK's been quite not going down that line a lot. The only one I'm aware of that's really gone into that heavily was when I think it was UCL, in the pandemic, they sent out home kits and had people really go into the kind of weighing of water as a method of titration at home because you can give someone a micropipette and balance for a lot cheaper and safer than a glass burette in their
Mhm.
kitchen. But for various reasons, we've basically we mostly use titrations in the schools. Plastic burettes oftentimes just
Oh,
for breakage reasons, but that seems to rule the roost. Like, no matter how bad it gets, no matter how much the pandemic knocked out, no matter how low the school's budget is, the one thing we can generally rely on in Scotland and the UK as a whole is that someone's done a couple of titrations to the point where they're sick of them. Even if they've done very little else in a school, they know how to turn a burette tap. That's the one grace of it.
yeah, I've seen a lot of papers on balances or gravimetric titrations, and yet I'm not seeing the pickup on it that I would have
Mm,
thought. And I've been curious why. If anybody's
yeah.
got a comment, that'd be great.
Yeah, I'd be interested to hear if anybody else has got experience with that, because my gut just falls back to the kind of school's perceiving of the balances as a one-off expense that they don't have space for. But hmm, hmm. I
So
am
far,
I
no
am gonna
comments.
take
Yeah.
a note of that somewhere. If only I was sat at a computer. Uh, there we go.
Since nobody's got a question, I'm going to pick your brain and everybody else's as well. I'm asking for a friend. I was at a conference last week and somebody asked me about a cheap gas chromatography instrument, sort of portable
Ooh.
that they could take into a lecture. And I think I've seen something on that outside of the research realm, but I can't remember where. Oh, okay. They were asking because they saw verniers and were asking if there were any others. So thank you.
Uh, yeah. No, I'm afraid as I'm stuck in first year in our large ecumenical fume hood free equipment free classes and my background isn't analytical science. I'm not aware of it, but that would be an excellent thing that was available.
Oops, just a sec.
Ooh, some cool things coming in.
Whoops, yeah, I'm just trying to copy these. I know they're,
Ooh,
if it makes you feel better, our first year course is about 2,800,
wow.
but the Canadian system's a bit different. So
Mm, no, very yeah, different. I always marvel as somebody that tries to do a little bit of kind of data collection, sampling, statistical analysis on interventions, and I'm dealing with maybe 30 people fill out a survey from a class of 150, and then I read the average North American study and just have a little bit of a cry about my sample size and significance. So you've got an amazing environment for doing kind of research like that.
yeah,
Ooh.
the vernier doesn't, I think it just uses air if I remember right.
Ooh.
I'm
I
taking down
shouldn't,
all the links from the chat, and when I send out the recording, I'll pass those along as well.
great. Yeah, I've been copying too, but um,
Ooh.
my analytical classes aren't so large. They were about 100 to 160.
Oh.
Uh,
Oh, no, that is an elegant elegant instrument. Yeah. No, as I
and I
say,
know
yeah.
I know Jim Grinius has done a lot with portable LCs, but yeah, the GC and I know they are available in terms of um, you know, field analysis and that type of thing. But yeah, just the teaching. So this will be interesting to look at. Thank you.
Yeah. No, I think Strathclyde on the research side has a very strong history of Raman spectroscopy, and we have some handheld Raman spectrometers that we use for materials characterization. Some students have used them for outreach projects. So again, quite nice. My own interest as an organic chemist is benchtop NMR. I would love one day to be in a teaching lab where we could have something, even a permanent magnet instrument that you. I love that you shim them with an Allen key. It's great. And
You've
again,
seen the analysis instruments.
mm,
Analysis has, I think they're up to 90 megahertz now for benchtop.
wow.
We have
Um,
one, but it has been a little bit of work to find the right compounds that the organic students can interpret the data. Um, but that's something our department has been working on. It's pretty cool.
yeah, I think you're pretty high concentration, like neat. Um, but it's still for first year classes, it gives them some access.
Mm.
Shannon, you haven't had any experience with your analysis instrument yet?
No, we just got it. It was like an add-on to the big NMR that we just had to get because
A little baby on the side.
was a paperweight for a little bit, and our synthetic organic chemist was shitting bricks, but we just got the benchtop. So I think they're just starting to look into what can we analyze with it, what kind of data will come out of it that we can use in the classes. So I think that's kind of our organic chemists summer project, is figuring out what it can do, but it's significantly cheaper than the big NMR. It
Now, was
wasn't
that an
super cheap.
analysis or somebody else?
I think it was an analysis.
Okay.
Yeah, that we had it quoted through and then got. Might have been something around like 50 or 60,000 Canadian. So it's not cheap, but it's not 600,000
Well, in
Canadian for
pounds,
the
that's
bigger
like what,
one.
a buck fit or a £5 50.
Uh, if only. I mean, these kind of things are fantastic, but I suppose it's interesting thinking about it on scale of trying to do outreach, not just by bringing people in to use the instruments or taking them out. The Royal Society of Chemistry in the UK for a long time had a program called spectroscopy in a suitcase. So they had a portable IR, ATR, and a few other instruments, and just took them around schools, set up for an analysis day. So people in a school who had done a synthesis could get their analysis for their examinations on an instrument that would just be inaccessible to them. So I'm a big fan of kind of portability and accessibility, as you kind of seen from the stuff. But this kind of stuff is great.
We've got GoMax, but I couldn't tell you if they still make those. They work forever, so maybe that's their problem.
I mean, there's something to be said for the best instrument you have is the one you already have. The best instrument is the one you already have. Our specialist analytical lab has a GC that is, I think, older than me, and it still works perfectly well. I think it plots on a plotter pen drive. But again, the students are getting great results out of it. So
Well, thank you, Patrick, for a great conversation about what you've been doing and what people are thinking about for affordable and portable instrumentation. Really appreciate it. I'll send out the recording and the links in a follow-up email, but probably not until Monday. But I am just going to drop into the chat again the information about next month's webinar, which will be about sort of modernizing the curriculum and topics that we might want to add for undergraduate analytical chemistry. And if anybody has any final questions, you're welcome to chime in. But thanks everybody so much for joining us on this Friday. And Patrick, thank you for correcting my time zone confusion.
no, I was I correctly assumed that it was this time, so we're grand. No, thank you all for it's been great to just sort of chat about these things. And yeah, I'll email you a copy of the presentation and any of the links as well that I mentioned from it, so you can feel free to send those out.
Thanks very much.
No, thank you. And yeah, I look forward to, as a non-analytical chemist, I look forward to sort of following the meetings and seeing how it all develops. And I'll attend as many as I can. All right.
Bye,
Thank you.